Good morning, everyone. A very warm welcome to all the distinguished guests, respected faculty members, research scholars, and students gathered here today to celebrate National Science Day 2025. To begin this auspicious event, I take this opportunity to invite our chief guest, Professor Kedar Singh, School of Physical Sciences, JNU, Professor Ishtiaq Ahmed, Registrar MANUU, and Dean School of Sciences, Professor H. Alim Basha, to kindly come and take their seats on the dais. I also request the conveners of the program, Professor Arif Ahmed, Head Department of Zoology, and Dr. K.R. Maruti, Associate Professor Botany, to please join us on the stage. This special occasion marks the discovery of Raman effect by the legendary physicist C.V. Raman, a discovery that brought India its first Nobel Prize in Science. Today, we come together to honor scientific progress and innovation, to seek the blessings of the Almighty. I now invite our research scholar, Mr. Fazle Rasool, for the recitation of the Holy Quran.
Assalamu alaikum wa rahmatullahi wa barakatuh. أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. والضحى والليل إذا سجى ما ودعك ربك وما قلى وللآخرة خير لك من الأولى ولسوف يعطيك ربك فترضى ألم يجدك يتيما فآوى ووجدك ضالا فهدى ووجدك عائلا فأغنى فأما اليتيم فلا تقهر وأما السائل فلا تنهر وأما بنعمة ربك فحدث صدق الله العظيم. شكرا.
Now it is our honor and privilege to felicitate our esteemed guests. We request our Registrar Sir, Professor Ishtiaq Ahmed, to present a token of appreciation to our chief guest, Professor Kedar Singh. We request Dean Sir to extend the honor to our Registrar Sir. We request Professor Arif Ahmed to present a token of appreciation to our Dean. We request Dean Sir to extend the honor to the conveners of the program, Professor Arif Ahmed and Dr. K.R. Maruti. Music and melody inspires us all. To elevate our spirits, let us now listen to the soulful MANUU Tarana.
ये बाबे शहरे इल्म है उर्दू ज़बान का, ये बाबे शहरे इल्म है उर्दू ज़बान का। आओ सफ़र यहाँ से करें आसमान का, बाबे शहरे इल्म है उर्दू ज़बान का। इल्मो कमाल फजलो शियारो शूर तक फैली है दिल नवाज महक दूर दूर तक। मिलता यहाँ निसाब है सारे जहान का, ये बाबे शहरे इल्म है उर्दू ज़बान का, ये बाबे शहरे इल्म है उर्दू ज़बान का। हर नक्शो रंगो बू से करो अपनी गुफ्तगू, आजाद दरसगाह की है ये भी जुस्तजू। सब फासला मिटाते चलो दरमियान का, ये बाबे शहरे इल्म है उर्दू ज़बान का। ग़र्बो जुनूब से होके शर्क़ो वो शुमाल से आगे बढ़ो ख़याल मिला दो ख़याल से। चर्चा हो कायनात में हिंदुस्तान का, ये बाबे शहरे इल्म है उर्दू ज़बान का, ये बाबे शहरे इल्म है उर्दू ज़बान का। फसले सदा बहार से बस्ती बसी रहे, मिलकर दुआ करो कि ये खेती हरी रहे, साया रहे सरों पे किसी साएबान का। आओ सफर यहाँ से करें आसमान का। ये बाबे शहरे इल्म है उर्दू ज़बान का।
I would like to mention that the MANUU Tarana is written by our Honorable Vice Chancellor. It not only resonates with our aspirations, but also instills a sense of pride in every heart. We are honored to have our Vice Chancellor with us today, Professor Syed Ainul Hassan sir. We request our Dean to present a token of appreciation to our Honorable VC. To set the stage for today's discussion, I now invite Professor H. Alim Basha, Dean School of Sciences, to deliver the welcome address and enlighten us about the significance of National Science Day.
Assalamu alaikum. Khush Amdeed. Respected dignitaries on the dais and off the dais, my dear colleagues, deans, directors, head of the departments, research scholars, students, ladies and gentlemen, adab. On behalf of School of Sciences, I extend a very warm welcome to our beloved Vice Chancellor, Padma Shri Professor Syed Ainul Hassan sir, for accepting our invitation and presiding this function. My heartfelt appreciation to our chief guest, Professor Kedar Singh ji, Professor and former Dean in School of Physical Sciences at Jawaharlal Nehru University, New Delhi, for accepting our invitation to deliver a keynote lecture on the eve of National Science Day 2025. I personally welcome you, sir. My sincere gratitude to our registrar, Professor Sheikh Ishtiaq Ahmed, for gracing this function with his presence. Thanks a lot, sir. I also welcome to our conveners of today's function, Professor Arif Ahmed and Dr. K.R. Maruti, for organizing this event. At the last but not the least, I welcome each individual for gracing this function with your attendance. I wish to add that National Science Day is the day when India honors the discovery of Raman effect, along with appreciating the contributions of our scientific community. National Science Day in our country is celebrated every year on 28 February to honor the discovery of Raman effect by Indian physicist Sir Chandrasekhara Venkata Raman, Sir C.V. Raman. On 28 February in 1928, Sir C.V. Raman made the remarkable discovery of the phenomena of scattering of light with molecules of matter. Basically, the Raman effect occurs when light passes through a liquid and some of the scattered light changes color. This happens because the light interacts with the molecules in the liquid, which alters its energy as well as wavelength. In simple terms, when light hits molecules, its wavelength shifts slightly, leading to this change in color. So, recognizing its importance, Sir C.V. Raman was honored with the Nobel Prize in Physics in the year 1930. With an Indian scientist becoming the first Asian to receive the Nobel Prize in any branch of science, it was a significant milestone for Indian science. So it placed India on the global scientific map. In the year 1986, under, under Prime Minister Rajiv Gandhi's leadership, the Indian government declared February 28 as National Science Day to honor Dr. C.V. Raman's groundbreaking discovery, the Raman effect, based on the proposal submitted by the National Council for Science and Technology Communication. So the idea behind this proposal was to celebrate the path-breaking discovery of Raman effect, as well as to encourage scientific thinking and awareness among the Indian population. Since the inception of School of Sciences at Maulana Azad National Urdu University, we are also celebrating February 28 as National Science Day by conducting various scientific activities, including invited talks and extension lectures. So this year also we have conducted 4 scientific activities for MANUU students, like essay writing competition, science short film making, photography competition, and science conceptual concept startup during this week only. At the end, I would like to record the special thank to the competent authorities of the university for providing financial support and their continuous guidance in organizing this celebration of National Science Day 2025. Once again, I extend my warm welcome to everyone for today's celebration. Thank you. Jai Hind.
Thank you, sir. We are honored to have with us Professor Ishtiaq Ahmad, Professor Ishtiaq Ahmad, Registrar MANUU, who has played a key role in supporting education and research at this institution. I now request him to share his insights.
Thank you very much. Good morning to all of you. First of all, I greet all our students, faculty members, research scholars on the occasion of National Science Day. Indeed, it's a great day that the entire nation celebrates in order to develop scientific temperament in the student, the scholars. And MANUU had been regularly celebrating this day by involving all our scholars, students, faculty members, and by, as Professor Alim Sahib said, that on this occasion we do conduct several essay competition, quiz, and many other competition among the students to ensure that their participation is recorded. I am happy that on this occasion, the university has decided to invite one of our colleague, Professor Kedar Singh Ji from Jawaharlal Nehru University. He is an eminent scholar from the School of Physical Sciences. He agreed to be part of this National Science Day celebration. As all of us know that these days, university is going through an important presentation, that is academic and administrative audit team. Entire university, entire departments, schools, they have presented themselves before the expert member to ensure that our academic and administrative activities are on right path. In this direction, I myself as registrar of the university, I have to present before the academic and administrative audit team before the expert. And I have to rush for this. I'm very sorry. I have to go to my office and then I'll have to take part in the presentation. Thank you very much.
Thank you, sir. It is an honor to have a distinguished personality among us today. To introduce our esteemed chief guest, Professor Kedar Singh, I invite Professor Arif Ahmed.
Assalamu alaikum and good morning to all. Honorable Vice Chancellor, Padma Shri Professor Syed Anwar Sahab, Registrar Professor Ishtiyaq Ahmed sir, Chief Guest of the program Professor Kedar Singh, Dean School of Sciences Professor Alim Basha, Convener of the program Dr. Maruti KR, distinguished guest, our colleagues and young minds. It is with immense pride and privilege that we gather today to celebrate National Science Day, an important occasion dedicated to honoring scientific excellence, innovation, and its transformative impact on the society. On this promising day, it is my great honor to introduce distinguished scientist and inspiring academic leader, Professor Kedar Singh, whose contribution to experimental condensed matter physics have left lasting remark on the scientific community. Professor Kedar Singh sir started his academic journey as an assistant professor in the Department of Physics, Institute of Science, Banaras Hindu University from 2004 to 2014. Currently, Professor Kedar Singh serves as Professor of Physics at the School of Physical Sciences and the Director of the Advanced Instrumentation Research Facility at JNU, New Delhi. His area of research is experimental condensed matter physics. His remarkable academic journey spans over 2 decades, shaping the future of numerous young scientists, having supervised 12 PhD scholars and currently guiding 6 more. His dedication to academic excellence is evident in his mentorship of 32 postgraduate students and 5 postdoctoral researchers. He has published over 152 research publications in international journals and authored 4 books and has a patent in advanced battery technology. Professor Singh has significantly contributed to material science and nanotechnology. His groundbreaking work in smart nanostructure, optical sensor, and metal halide materials had led to advancement in energy storage and functional materials. His expertise is widely recognized with an H index of 31, I-10 index of 92, and over 3,100 citations to his credit. Professor Singh has global academic outreach, including prestigious fellowships such as Wyckoff Fellowship availed at Florida, USA from 2008 to 2009. Raman Fellow for Postdoctoral Studies in US under US Century Knowledge Initiative Program 2013 and 14, availed at High Magnetic Field Laboratory, Florida, USA. His influence extends beyond research, serving in key academic and administrative roles, including Dean of School of Physical Sciences, JNU, New Delhi. He is also an active member in various national and international scientific bodies such as Inter-University Accelerator Center, New Delhi, and IUCA, Pune. He has held several key positions, including member of Executive Council at JNU, member of JNU Court and Academic Council, Empowered Committee of IMC JNU, and many more. As a dedicated leader in advancing research infrastructure, Professor Singh has successfully led multiple high-impact research projects, securing a significant funding of rupees 2.5 crores and 4.6 crores under DST FISH program during his tenure as a dean. His relentless pursuit scientific excellence continue to shape the next generation of physics and researchers. On this Science Day, as we celebrate the spirit of scientific inquiry and innovation, we are truly honored to have Professor Kedar sir with us, an exemplary scientist, mentor, and visionary leader. We are privileged to have an opportunity to hear him on the topic Raman effect and its importance in current science and research development. With his dedication to advancing knowledge and fostering cutting-edge research, serving as an inspiration to all of us. With these words, I humbly request Professor Kedar sir to share his scientific insight and visionary ideas with the audience. Thank you. Please, sir. Thank you.
Good morning to all. Respected Padma Shri Professor Syed Anur Hussain, Honorable Vice Chancellor, uh, uh, Maulana Azad National Urdu University, and Professor S.K. Taqi Ahmad, Registrar MANUU, and Professor S. Ali Basa, Dean, School of Sciences, MANUU, Professor Arif Ahmad, and Dr. Maruti K.R., convener of this today event, and Dr. Sadiq, because I taught him, and faculty members, students, and also media person. Thank you very much for inviting me to deliver a lecture on today, Science Day. Science Day, if you see, as Professor Basa told the things, this is not a simple thing. Science Day, if you see, this is a festival for our for science or scientists. This is only discovery in India. Professor C.V. Raman done really. Here, if you see nowadays, a lot of applications of this is the Raman effect. This is the nowadays this is a Raman spectrometer. By the help of this, lot of you can say this is the things are going in science, research, and also by the help of this we can know the nature of this is the material, which type material, what is the nature of material, not only in research. Nowadays you can see this is the portable, you can this is the Raman spectrometer. Then you can know about drugs, and also a lot of medicines we can analyze through this spectrometer. So, and it's by this spectrometer we can know about different finger things and this. So this effect is very important, and applications. Or if you see this a lot of effect in science for application wise, this is the Raman effect. So that's why we celebrate this is the Science Day on 28th February every year, and also Government of India also in this year also they celebrating this Science Day in this is the high end you can say. And for why we have to celebrate Science Day in university level, if you see science is so important. If you see other subject, this is the, you can say physics, chemistry, mathematics, biology. For this we have to have how we can develop science in the in our lab, how we can understand the things through science, because these are a lot of things can be there, that how we can understand through science, and how science, then how we can give we have some queries, so through science we can have solutions, we can give the we can have answer of the this is the queries. So there's as told, this is a lot of quiz going on here in the occasion of the Science Day. So this is good. At least student will come forward and they will know about science. Then how science is always true. If you see, if this is the science, then how a student can attract through this is the different activities related to science. So that's why this is very important. And yeah, this is a very good gathering here. People are this is the students and faculty member gathering here. So this is good. This is it is showing the how your interest in science and how things can work in science. So my full this is the lecture, this is the, I will give through slide how things will work, what the Raman effect, how we can understand the applications. This is my slide. Thank you very much to again to come here.
Thank you, sir, for sharing your insights. We are honored to have with us Honorable Vice Chancellor Professor Syed Ainul Hassan, sir. Just as science is fueled by research and innovation. I'm sorry.
Thank you.
Okay, sir.
It's all right.
Yeah.
Bismillahirrahmanirrahim wa bihi nasta'in. Professor Kedar Singh, today, JNU thread in MANUU's tapestry. Let us welcome Professor Kedar Singh. Colleagues, Professor Kedar Singh joined very late, in fact, and even the School of Physical Sciences came up when I was quite mature teacher of JNU. See, they are born before my eyes. So that's how. It's not very, very old, rather, in fact, but they have done a lot. School of Physical Sciences, including they are good cricketers. Now, every day is a science day. What is there? But everyone is not C.V. Raman. So today is a special day, 28th February is a special day dedicated to great scientist C.V. Raman. And I believe, we can't survive without sciences. Let me explain my plight, in fact, what happened, in fact. An overall impression. When I was a student of, say, high school, 9th standard, then we were asked, in Uttar Pradesh, high school, it's not higher secondary, it's high school and then intermediate. So in high school, for the first time, after, getting another class, 9th standard, then every, student was crazy enough to go for sciences. And there were only 3 subjects, one physics, chemistry, and biology. And some, a crowd was asking for the same combination. In fact, then I also applied for the same combination. But later on realized that I don't have any scientific instinct within me. I was thinking of switching over to another discipline because I was more interested in economics and history. But history was not there. So civics, economics. This was, combination of the time. Anyway, somehow we approached the principal, and principal himself was MA in history. So therefore he agreed, and somehow we collected 5 students, to opt these, combination. Now what happened later on, it continued, until my graduation. This economics history. But later on I realized that what is not science? After all, these are also sciences. And today, we can't survive without having a set of mobile which is providing everything, whether history or economics, data, mathematics, calculation, including anthropology and philosophy. And therefore, अब मैं अगर कब्र में चला गया और फरिश्तों ने मुझसे पूछा कि तुमने मोबाइल देखा, तो मैं कहूँगा हाँ बिल्कुल देखा। डेटा कलेक्ट किया, मैंने कहूँगा हाँ कलेक्ट किया। और अगर कहीं मैं ये भूल गया कहना, मैंने कहा नहीं मैं बहुत फायदा नहीं उठा सका मोबाइल से, तो वही फरिश्ते फिर रिपीट करेंगे कि तुम हमारी नेमतों को कब तक ठुकराओगे, कहाँ तक ठुकराओगे। फबिअय्यि आलाइ रब्बिकुमा तुकज़्ज़िबान। This is how you see we can discuss sciences. As I said, every day it's a day of sciences. ये जो हाथ हमारा उठ रहा है इसमें भी कोई ना कोई फिजिक्स है. And I'm sure you will realize, and you must have read out recommendations under National Education Policy where integration of disciplines, they are talking about integration of disciplines. So Salman Sahab and Maqbool Sahab should not say that we are scientists. Okay? You see, rest of the professors can also claim that, okay, we are also scientists. Anyway, colleagues, girls and boys, I'm not here to speak much because the speaker is already here and you will listen to Kedar Singh ji. But let me just remind you that this is the best opportunity. These are symbolic expressions when we celebrate a day. We say that, look, this is Science Day. This is Day of Education. This is Day of Foundation. This is Day of Maulana Azad. But yes, every day is important. Remember, you have to apply, and if you don't apply your intellect, nothing you can achieve. In order to achieve something, you should go beyond the horizon. Don't confine yourself to one segment, one section. Study in isolation is very bad today. You should study area studies also. Area studies, when you are doing physics, you must know relevance of chemistry. You must know relevance of mathematics. You must know relevance of calculations, data collection, and the kind of research is going on in your country and outside the country. Try to visit outside the country also. There are laboratories. There was a time when Baghdad was considered as the best place to interact. But now there are so many. You go to a city, to a university, you will find scientists, scholars, intellectuals working together, trying to resolve issues, trying to formulate things. All these things are happening. But what for? There is another set of goal. When you achieve something, you become a nuclear scientist. You can produce something for the benefit of mankind. But same thing can destroy humanity. Einstein was perturbed with the idea of, seeing Hiroshima and Nagasaki. It was great setback to Einstein, the one who created relativity and later on realized that, look, it was dangerous for the mankind, for entire humanity. He was ashamed of producing something. I'm not producing something, but misuse of something which was good for the country. And today, you must set a goal in the sense that what ultimately your target is, how to make use of your knowledge. Knowledge, if you are making use of knowledge in a very, very positive manner, it's all right. But don't go negative. Like, when you are asked to perform something, but halfway down, you perform something other. हमें यकीन था तुम सर उतार लाओगे. तुम्हें बैटल फील्ड में भेजा गया था कि तुम जाओ सामने लड़ो, मार दिए जाओगे या मारोगे. बैटल फील्ड का नाम ही यही है. हमें यकीन था तुम सर उतार लाओगे. किसे खबर थी कि चादर उतार लाओगे? But you did something else. संभल ना पाएगा, and then again blaming others. संभल ना पाएगा जिस रोज तुमसे अपना मकान मेरे मकान के अंदर उतार लाओगे. And then you will say this is my house, and then the clash of interest goes on. So therefore, you remember your target. And there are many people, C.V. Raman, including C.V. Raman, Abdul Kalam, they were great scientists, Einstein. But don't consider that they are the ultimate ones. Someone else will come. Someone else will come and occupy the same place one day. You will become someone. You are not identified. You are in the crowd. You are not identified. But one day, there is a possibility that you will be recognized. Your work will be recognized. So, संभल ना पाएगा जिस रोज तुमसे अपना मकान मेरे मकान के अंदर उतार लाओगे. मैं जानता हूं खुदा हो मगर कहूंगा नहीं. इसी दुनिया क्या करती है? खुदा बना देती है. बड़ा सबसे बड़े आप हैं, आपसे बड़ा कोई नहीं है. तो फिरदौसी ने कहा था कि मैं आजार मूरी के दाने का शख्स, एक चींटी को भी मत सताओ, इसलिए कि उसकी जान भी उसके लिए प्रेशस है ना. और खुदारा बरौन बंदे बख्शाइशस के खल्क अज वजूदस दर आसाइशस. खुदा उसी बंदे को नवाजता है कि जिस बंदे की वजह से सारी मखलूक आसाइश में रहती है. तो मेरे मकान के अंदर उतार लाओगे. हमें पता है खुदा हो मगर कहेंगे नहीं. खुदा हो मगर कहेंगे नहीं. तुम आसमां से पैगंबर उतार लाओगे. Otherwise, you will become someone and start searching for producing something which is not really conducive for the health of society. So therefore, confine yourself, move forward, go with the sciences, and pass it to another generation. That's your duty, and that's how you will be remembered for a very long time. Thank you very much.
Thank you, sir. Your words have truly inspired us, and we deeply appreciate your time and wisdom. Mic की जगह में distract हो रही हूँ. Now we have arrived at one of the most anticipated moments of today's event. I invite our esteemed chief guest to deliver his lecture.
ठीक.
नहीं ये चीज इस तरह को आगे इस पर पीछे ये पहले आ जी पॉइंटर सबसे आगे आपके पॉइंटर नहीं है सामने सबसे आगे
Yeah, welcome you again. This my talk is this is the Raman effect and its importance in current science and research development. It means this is the today this is the Science Day, and Science Day celebrate only this the Raman effect. So if you see in this year, this is the government of India. This is the empowering Indian youth for global leadership in science and innovation for Vikashit Bharat. So this is the theme of this year. Then how this is the science. So that's why we are celebrating here. So let us first start from Science Day, and if you see, just as I told you, this is the every year we Science Day celebrate on this is the 28th February, and why this is the, if you see here, yes, if you see Professor C.V. Raman, discover, this is the Raman effect. If you see Raman effect, this is the, if molecules vibrate, then what will happen? This is the, uh, around 10,000 molecules. One molecule have, different properties. Most of molecules have, this is the same property. There is the, but some molecule have different property. They absorb some energy, photons. And so this is the, if you see, this is the vibrations will be there. So most of molecule done vibrations, but some molecules means around 10,000 molecules. One molecule will absorb, this is the energy. So this is the, this is the Raman scattering, and so that's why wavelength, everything will be changed here. Then what will happen if you see here, and and Professor C.V. Raman also got Nobel Prize in 1930 in the science facts. He was so confident. Okay, after discovery of Raman effect, he was so confident that this year I will get Nobel Prize. So this is the how people will how he believe on science. Okay, this year I will get Nobel Prize. So then also he declare this year definitely I will get Nobel because I discover this is the great the Raman effect, or this is the discovery. How does it work? Oh, if you see here, this is the we taking this is the one molecule, but this is not only one molecule. This is the 1,000, 10,000, or the more huge molecule. What will happen here? This is the laser. Beam will come. This is the have wavelength, and this will strike here. This is the molecules, and molecule also vibrating. If molecule is not absorb anything, it means then wavelength will not be changed. And what will happen? This is known as this is the relay scattering. Here this is the, so things will come. This is the relay scattering. If molecule absorb, so then after this is scattering, wavelength will be changed here, and you can say the wavelength can increase or decrease. So these things are two things are here. This is the, if this is the if wavelength, if you see this is the this is the laser wavelength or incident wavelength here, or this is the scattered wavelength. Scattered wavelength is less as compared this is the incident wavelength. This is known anti-stock Raman scattering. These things are come here. Same thing here. What will happen if scattered wavelength is higher as compared this is the incident wavelength. This is the laser. This is known stock Raman scattering. So this is change of wavelength. It can be decrease, it can be increase, but this is the, as I told you, this is the around 10,000. One molecule have such type property. So this is the property of molecule. This is the property of material. So that's why we can identify a lot of things from help of this is the Raman scattering. Then if you see here, then if you this is the Raman scattering, this is the some different energy state will come here. Then this is the things will come. This is the, then how these things. If you see for relay scattering, this is the things are. If you go for stock line and anti-stock lines shift, then if you see stock, it have higher wavelength as compared this is the intensity as compared this is the anti-stock. You can see it here. So these things are here. Then if you see the photon will go up. Then after some virtual images, it will go down. So this is the Raman scattering. But if there is no change, this is the elastic scattering. Here, this is also inelastic scattering. Things will come here over here. Then we can, yes. If you see, as I discuss about, Raman spectrometer. Raman effect is okay. But what is the application? This is important in science. So that's why you need some tool. You need some, tool. So tool is the, Raman spectrometer. Then how does it work? This is the, simple spectrometer. Then you can see it here. Then if you see, yes, this is the laser beam. Then this is the some special type mirror. This is the dichroic mirror is here. This is the sample where we will be the study. Then what will happen? It will go here. So most of you can see this is the exciton, laser beam and radiate scattering. Everything will filter here. Then what will happen? This is the only Raman scattering. Light will go here. Here there's some beam, filter, and here this is the mirror. The mirror will here. Then we can change, some adjust, from the moving mirror, and this is the detector. Finally, we will get, this is the Raman scattering through detector. Then we have, I will show you some spectra there. Then these things will come. The most of thing, if you see, here will come only Raman scattering thing will come here. Then here most of thing will, this is the absorb or will be filter here. So this will come here. And how these things will come, I will show you here. This is the, yes. As I told you, I am working as a director AIRF, Advanced Instrumentation Research Facility. We have, this is the, this is the AFM Raman spectrometer. This is the unique thing. By the help of this, we can take images. Also, we can see, this is the, Raman study. So this is the, spectrometer here. Then you can see. And just I want to show you, this is the, this is the AFM image. The image by graphene take, this is our, JNU. This is then this is the, if you see, Raman, the spectra of graphene. You can see this is the, then you can see these things are, you can get the peaks are here. These peaks are coming due to the vibration of, this is the molecules. So absorbed things are coming, this coming that due to the vibration of the molecule. That by the, we identify these peaks by the help of this peak. Then we can know that about the nature of material. Some most of things how we can know through this. So this is the here. This is the AFM image. By the help of this, we can know the morphology and the number of layers through. Then we can put some layers somewhere. Then we will get it here. So this is here. Then yes, if you see the applications, start the application of the Raman spectroscopy, or you can say this is the Raman scattering. If you go first, application the fundamental, this is the interaction. If you want to know the structure of the water molecule, water molecule has a lot of structures. By the help of this, we can know. And ionic liquid now we are using for different type ionic that we can know about and its mixture. The water by the help of this is the Raman spectrometer, we can know about this. Other is the material size, huge. Nowadays you can say this is the carbon material. You need this is the Raman spectroscopy to investigation. 2D materials, MOS2, you can say WS2. For this you need this material and other also material. And if you see for food, now the food industry, because if you want to know where this food is, then how they can check the food. Then this is the by the help of this is the Raman spectroscopy. Nowadays we can have tabletop Raman spectrometer. By the help of this, we can know about the dairy products, their coffee. By the help of this food, we can know about this. Fourth will come, this is the forensic science, anti-crime. If you see, then if you want to know some fingerprint, this by the help of this, this is the Raman, spectrometer work here. If you go for airports, custom officer has, this is the small box. This is nothing. This is the Raman spectrometer. By the help of the on spot, they can say this is the drugs have this composition. By the help of this is the Raman spectrum. So this is the and also some examination identification of the ducts, as I told you, and this is the reduction of the explosives. Well, if there is some explosive things are there, by the help of Raman spectrometer, you can find this is the explosives are here. So these things are here. Other is the biological application. If you see in a lot of application in the biology, this is the bio liquid and the cancer detection, because these are some cells are there. By the help of Raman spectrometer, if you put the some cells there, then the cell different type nature. By the help of this, you can know this is you can detect cancer and diabetes, these things. And also environment, identification of the nuclear material pollution, then you can also detect the fox pollution by the help of the Raman. So there's a huge application, Raman spectrometer. And now I will come on my, this is the, yes, as I told you, this is the AIRF, this is the Advanced Instrumentation Research Facility. Please go on, this side. This is the w.jnu.ac.in AIRF. Here we have very good sophisticated instrument, not only for physics, this instrument for chemistry, biology, life science. Here is the very minimum, this is the user charge. By the help of this, then you can get, measurement, characterization of, our materials. So this is a very good opportunity. This is not only for JNU student. Outside, JNU student can come there, then they can get characterization. So this is just for information. Then you can take advantage of, this is the AIRF. I am looking this facility nowadays. So there should not be very big problem. Come over here, then see the web page. Then you will get, about students, these things. Now I am coming on my research part. If you see, this is the nowadays you can say the nanomaterials. Nanomaterial, this is a low dimensional material really. If you see number of atoms reduced there, then property of material change, huge change, because surface to volume ratio this change, so that's why property change. So this is the, if you see, we can classify materials, this is in three parts. This is the bulk, this is a three-dimensional material, you can say. Then this is the 2D material, two-dimensional. Here, whatever density of state, you can say this is the change, huge. Then you can say, and the quantum number. Then if you go for quantum wire means electron will you move in the one direction. This is coming here. Then if you go for quantum dot, size is below 10 nanometer. If you see, quantum dot has a huge applications. This is the subcategory of this nanomaterial. But by the help of this, if you change the size, then what will happen? Optical property also change. Means band gap change here. So there are a lot of things you can control. So this is the nowadays very useful. So this is here. Then how? If you this is the density of quantum states, number of atoms. If you reduce the number of atoms, then what will happen? This is the bulk material. You can say stage here. But if you go for quantum dots, it will come three states. If you molecules, concept of homo and logo will come here. If you go for atom, this will come. So sometime this is a quantum dot, or the nanomaterial, which known as this is artificial atoms are here. So these are here. Yes. Why you see the quantum dots? Now this is the, if you in 2023, the three scientists got Nobel Prize in development of quantum dot. So this is the, if you see, the then huge application, huge the fundamental things are coming here. So this is the three scientists. This is the you can say this is the Mugli ji, Verdi, and Lewis, and you can say this is the Alexei. So they did a lot of work. This is the quantum dot. Then it will come here. If you see, this is the then they find this is the CDSE quantum dot. By the this is the Lewis did this work, and this is the Alexander. He found this is the some colloidal quantum dot, and these things are coming here, and quantum confinement. But great work done by this is the Vivendi. He used some some precursor here and some chemical thing. Then he put some this thing make crystal here. Then heat it again. A lot of quantum dot he got it here. So this is the about this is the material, and this how does you can see the quantum dot. So this is very simple. This is the, this is a nano crystal. You can see this is a different color. Material is the same, CDSE quantum dot, but this quantum dot dissolve in you can say in the some you can say some carbon, this is the things. Then you can see here the different size of quantum dot is showing different colors. Because why? Because here this band gap is changed here, so this is coming here. And if you go here, so this is the some magnetic material. You can say if you dope some magnetic material quantum dot, then what will happen? This is non-dilute semiconductor. Here, what will happen? Magnetic properties also include here. That is showing dilute quantum dot. Here, what will happen? Here, ions create intentional defect and alter their optical properties, magnetic property, and electronic properties. So this is the issue. This is not a functional material. How you can functionalize the quantum dot through doping some 1 or 2%. This is the ionic magnetic ion. So this is the function here. If you see the what is quantum confinement, this is very simple. If band gap widening there, what will happen? Then the electrons and hole will confine in a particular this is the area. This is the quantum confinement here. Here you can see this is the it can be two types. Hole electron and hole combined there. This is known the excitons really. This is the big quantum confinement here. What will happen? This is the Bohr radius is small as compared. This is the size of quantum dot here. What electron and hole will confine here, and center of mass of the is confined. So this is not observed more. Strong quantum confinement here. Bohr radius is equal to this is the size of this is the dot. Then what will happen? Electrons and hole they will confined the different state here. So here what will happen? Electron and hole can individually move here. So this is the strong quantum confinement effect. Then if you want to do some work on quantum dot, so it's a very simple thing. If you want to know this is a quantum confinement or not, so this is a very simple experiment. You can take absorption spectra by the help of absorption. If you are able to get this peak is known as excitosome peak, then we can say this is the quantum confinement occur here. This is the quantum material. So these things are here. Then also if you change the size here, then whatever excitation property will also be changed here. So this is the things are coming here. So this is the by the help of this you can do about this is the quantum confinement, and also you can identify formation of quantum material not quantum dot by the help of this is the absorption spectra of quantum dot. Other is the you can say sorry. Yes, other is the PL spectra. If you take the dissolved quantum dot in some organic solvent, then if you put it this EV region, then you will see things are coming. Then this is showing glowing in different wavelength, and this is the PL spectra. This is coming also showing the mono dispersed things are here. But if you come here, yes. Band gap. If you see the band gap on the quantum dot, this is a change up to 10 nanometer. You can see it here. After this, there is no change of band gap. So therefore, we consider quantum dot up to 10 nanometer. After this, it can be this is the nanomaterial, but not quantum dot, because here band gap would not be changed here. And other, if you see, yes, how we can synthesize quantum dot? There are two. This is the method are there. One is the this is the bottom to up approach. By the help of this is the non-colloidal synthesis. Here we will assemble number of this is the atoms or molecule here, and this is the basically it's a chemical. This is the chemical method. Here there is no extreme condition. We can synthesize quantum dot. Other is the top to down. Here we will reduce the number of atoms here. So here this is the way is the this is the electron beam lithography and molecular beam lithography. By the help of this, we can also have quantum dot. But here we in the top to down approach, we cannot control this is the size of quantum dot. But here we can get pure quantum dot, and bottom to up because we are using some chemical here. So here we will get some impure quantum dots here. Other, this is some application of quantum dot also. If you see the huge application, you can see nowadays, the quantum information, wireless communication, this the cameras, TV, bulb also, you can say LED bulb, and this is the solar cells and ducts delivery, lot of application. You can see this quantum dot are a lot of applications. Other is the okay. Just now I want to show you my work when I was in US. The first work, this is the chromium dot CDS. Oh, this is the CDSE quantum dot. If you see this is the work. Then you can see here. This what we do. We take CDSE quantum dot. We take this is the you can say CD10 cluster, and we do for chromium source we take chromium chloride here. Then we combine this. This is the 40 ml hexadiamine, this is known HDA at 120 degrees centigrade nitrogen. This is the system here, nitrogen flowing here. Here this is the 3-neck flex, and here we stirring here. And reaction, this whole is in the nitrogen. The reaction is conducted 220 degrees for 6 hours. Then we dope here 0.6% chromium in CDSE quantum dot. Then you can see, this is the adjacent spectrum, XRD. You can see it here. This is the XRD is coming here. Then you can say the doped or undoped. Adjacent spectra, you are getting this peak here. It's a very good peak. This is the quantum confinement for dope. This is the TAM image. The particle size, the bunch of images here. The particle size is about 3.1 nanometer. So this is coming here through this thing. Then we study. This is the EPR, electron paramagnetic resonance. For this is for we can know about this is the peak is coming here. Then you can say when we go for room temperature to 10K, what will happen here? This is the then peak is split into 3 parts. You can say here this is the for different temperature, different frequency. Then we calculate plot frequency versus field. Then we get G factor. G factor is corresponding to chromium 2 and chromium 3 doped in CDSE quantum dot. So this is a lot of chemistry are here. Then we done magnetic measurement. This is the zero field cool and field cool. Then you can say this is the zero field cool and field cool, both are mixing, cutting at this is the room temperature. So this is the indication of the room temperature ferromagnetic CR CDSE quantum dot. And if you see here, then we take 1 upon chi here. So then this is showing some transformation. This is the superparametric state. This is the here the quantum superparametric state. So this is very important here. Then this is a MH curve, magnetization versus magnetic field. Then you can see that you will also able to get the hysteresis here. The hysteresis showing some we are getting hysteresis at room temperature. So this is the confirmation. It is showing this is a room temperature ferromagnetic chromium dot CDSE quantum dots. So this is the observation. Other material we take iron dot ZSE quantum dot different. Here what we do, we take this is the ZSE quantum dot. We take iron 1%, 5 and 10%, and this is the dot size 1.8. This is the very very fine dot is here, and this is coming. This is dot is size 1.8 nanometer. Then we dig this is the EPR. By the help of EPR, we are able to get iron 3 is doping in, this is the ZSE quantum dot. And after this, what we see here, this is the we take magnetic measurements. This is the DC speed. This is the ZFC and this is the zero field cool and field cool. Then you can get it here. Then different concentration. If you see here, this is the Willokin temperature. This is the Willokin temperature here. Here, this is the Willokin temperature. You can see Willokin temperature is going to increase by the doping of this is the iron here. So this is the good indication for Fe doped ZSE quantum dot. Then also we investigate this is the AC susceptibility. Also the AC speed for chi double dash. Then you can see this is the at higher concentration of the iron. This is the this peak is going to emerge here. So this is the some you can say some transition. Then which type transition we confirm by some criteria. This criteria is known by those criteria. If you see these things will come here, then if you see this is the, if this is for spin glass, then Maidos parameter will be less than 0.1. If this is a super material, this is the, it will be Maidos criteria will be, this is the greater than 0.1. Then you can see here, this is the iron concentration 1%, 5 and 10. For 1%, it is showing superparametric material, but if you go for 5 and 10%, this is showing, this is the spin glass behavior. So this is the, finding of, these things. Then if you go here, then the same thing is supporting here. And other is the, quantum dot. Most of time, this is the, if you see, quantum dot, this is, if you see, diffused, because the number of atoms is less, and so this is the unstable. So then if you make some core shell quantum dot, so the stability increase and application is also increase here. Then how then we prepare, so this is the core shell. Suppose this example CDSE, CDS. The CDS is the core here, CDS is the cell. Over, this is the CDSE. And the criteria is this band gap, this is the core, quantum dot is small as compare, this is the cell. So these things will come, there are two types. Then we here take, this is the CDSE B205 core cell quantum dot here. Then what we do, we take, the CD10 cluster. Then we take, the vanadium pentaoxide as a, this is the, it's a source of vanadium. Then we get, this is the core cell, this is the quantum dot here. Then how we will confirm these things are here? We take, this is the 10 milligram and the 20 milligram, CDSE B2, B205. So this is a thick and thin, quantum dot. How we will check it? This is the very simple things are here. This is the absorption spectra. We are able to get, this is the, this peak, this is the absorption peak. Then we can say the quantum confinement is occur here. This is the quantum material. Then if you see the peak hue shift, this hue shift cannot be cannot happen by doping. So it can be cell over, this is the CDSE. So then you can see, so this is the hue shift are coming here. Then you can say PL spectra, there is no change by, cell over CDSE quantum dot in the PL spectra. So this is good for, this is the optical application. And, this is the time decay measurement femto is also here. Then you can see here, this in this table. Then if you see here, for quantum yield, for, this is the only 3 for CDSE. But if you take, this is the CDSE B205 quantum yield increase here, 11 and 15. And time decay also increase here. So then we can say this quantum dot is the stable as well, and also quantum yield increase. So this is the optically also applicable. So this is the conclusion of, this study. Other also, this is the XRD here. XRD confer, this is the formation of material. Then also we record some, Raman spectra. If you see here, for, yes, Raman spectra, if you see for CDSE, we are getting, this is the peak LO and 2LO peak is coming here. Then this is SM2 peak. So this is the for CDSE. But if you go CDSE B25, this is the SM2 peak completely disappear. This is happening due to, this is the cell over CDSE quantum dot. So this is the, we can conclude by the help of, this is the Raman spectra. These things are, other things are coming same here. So this is there. And the other is the, we take time wave. Time wave is the direct evidence of, formation of the core cell quantum dot. If you go for CDSE, this is only size is 3 nanometer. CDSE V205 average size is, around 4 nanometer. But if you go for CDSE V205 thick, size is about, 6 nanometer. Here 3 nanometer are the core, or 3 nanometer are the B205 cell is coming here. So this is the things are here. Then we done ultra fast transistor spectroscopy in the NPL. If you see, this is the showing. If you go for CDSE, it is showing, this is a single bit. But if you go for CDSE B205, it is showing, this is the double things are here. Then by the head, this is showing CDSE showing the direct transition. If you say CDSE B205, it is showing direct as well the indirect transition. So we conclude here, this is the electron cooling rate decrease here. by the CDSE V205. If electron cooling rate decrease, it means such type material can be useful for, you can say, photovoltaic application. So it means CDSE V205 also useful for photovoltaic applications. And other applications, this is very simple, biocompatibility. If you see CD, this is the heavy metal is there. So CDSE V205 is the toxic. CDSE toxic here, but if you want to know CDSE B205 core cell is a toxic about toxicity, then what we will take, some cells are here. Then by the help of this cells, we check biocompatibility. If you see at the biocompatibility of the CDSE B205 is higher than CDSE. If you go for higher concentration, CDSE biocompatibility only 5%, CDSE B205 this is about 50%. It means this is more biocompatible as V2 CDSE V2 core cell quantum dot, more biocompatible as compare of, this is the CDSE. This is the other type quantum dot, zinc, gallium, sulfur quantum dot. Here we take, we change the ratio of, this is the zinc and, this is the gallium here. These things are coming here. And here what you can see, this is the, we calculate band gap. Here band gap is about 3.1 nanometer. PL spectra is showing, different, you can say this is the peaks here. So this is showing, some intermediate, this is the, band gaps are here. And particle size is about 3 nanometer. So this is, then this is the, we can say femtosecond things are coming here. So we conclude here, if you see this is the zinc sulfide, band gap about 3.49 electron volt. If you go for gallium selenide, band gap at 2.5 electron volt. But if you take, this is the zinc, gallium and, sulfur, band gap is about, 3.1 nanometer. So this is the showing, this is good for, photovoltaic application because this is showing different. So these things are here. My other work, this is the this is the nowadays, this is the, peroxide quantum dot. Here, what we take really, this is the entirely different work I am working with. So if you see, we take here, this quantum dot is very useful for, photovoltaic application and other application also. Here, what we do here, we take, this is the CSPVBR3 peroxide quantum dots. Here how we can synthesis, first we have to prepare selenium, cesium oxalate. We take, this the cesium thing, cesium carbonate and this thing. Then after this we dry at 120 and finally 150 we get, this is the cesium oxalate. Then this is in stock. Then we add, a PVBR3 and oxalic acid and, this is the oxalic amine. Then put it here. Then we throw injection. We put it here. By the help of this, we get, this is the CSVV peroxide quantum dot. By the hot injection, with temperature 180, then we throw injection. We put it here. Then this is change is showing here. Just I want to show you some XRD. This is coming very good XRD. This is the this is the EV spectra. You are able to get, this is the peak here. This is the quantum confinement. PL spectra is very sharp. PL spectra is coming here. Then you can say, and size is about, this is the 10 nanometer, 10 or 11 nanometer by 10, and this is the, it is showing also very crystalline size, and size it is coming here. This is the some gap here. Okay. Just I want to show you, this is application. Then we did, some magnetic measurement, CSPVBR3 peroxide quantum dot. Normally quantum dots should not show any magnetic properties because this is the dimagnetic material, but due to some defects it is showing some, magnetic property. How we will investigate this thing? This is the first, just if you see, yes, this is the MH curve. You can see this is the temperature versus, this is the magnetization. Here what you can see, then if you see here, this is the, then this is the different temperature. This is the zero field cool and field cool. You will get some, this is peak coming here. It's should not come if, but you can see this is also come if you increase the field, peak also emerge more and more. Or this is the MH curve. This is showing some, at room temperature showing the diametric property, but if you go for higher low temperature, it is showing some ferromatic properties. So this is showing some transitions here. Then we calculate, this is the error to plot is also conferring the same thing, but we calculate some parameters through some formulas. This is the this is the different magnetic parameter. Then you can see by, if you this and temperature magnetic parameters, you can say this is the showing some change. You can say at this is the 156 the change. So this is change is coming due to some magnetic phase transition. The magnetic phase transitions are coming here, so this change are also coming here. This is the huge change. Other how we can explain this is happening latest distortion in crystal structure in VR host CSPB VR3. It means some latest distortion is happening here. Why it is possible? This is if this is a dimagnetic material, PB2 and PB2. This is same valency is a dimagnetic, but this is not case here. The PB2 and PB plus 2 and this is PB plus 1. So most of things, the parameter things are coming here, and this is the PB2 and this is the 3. So this is the balance mismatching coming here. So we are getting some parametric material here. So this is the things are here. Other work, this is the, then with some, this some thermal property also. If you see the thermal property, then this is the, some TGA. TGA, we get different peaks, we get it here, then we convert, things are here. Then we take, this peak by some kinetic parameters, by obtaining, this thing, then we get, this is the activation energy, gives free energy, enthalpy and entropy. This is the change here. And by the help of this, what we get here, the change of this thing, then understand of the thermal stability and degradation mechanism of the CSP VR3, facing through application in the advanced technology. Because we also know the thermal study of thermal investigation of material. So then we can use the material for the devices here. So, and my last work is this. This is the EMI shielding material. Nowadays, if you see a lot of electronic gadgets, you can see it here. Then they have some electromagnetic wave. Then how you can prevent your this is the electronic gadget, especially you can take a mobile phone also by the EM waves. So then for this you need some EMI shielding material. This material should be flexible, lightweighted, and also cost effective. So then we how we can study this, we can study through this is the vector analysis, vector network analyzer. This is the instrument. By the help of this we can study. Then how this is the some 2D material, MOS2, this is the layered material, this is a lot of property. Other the graphene, it is showing honeycomb structure here, then hexagonal honeycomb structure. Then if you see this is the lightweight material, and these things are here. But if you take RGO is considered as a harvesting, or this is the EMI wave, and this is the RGO surface and its edges pure graphene. These things will come here. We prepare, this is the, MOS2 RGO gallium doped nano composite here. We take, gallium RGO here, then gallium composite, then we heat it, then this is the autoclave, then we prepare this thing. This is the XRD coming here. Then this is the, we take, Raman spectra. How we can use the Raman effect in research, then you can see it here. Then we get, we enlarge this, the D and G peak. This is the thing, other peak is coming here, but D and G peak are coming here. Then we take the ratio of I intensity of, D peak and intensity of the G peak. Then you can say this ratio is going to increase here. If you dope, gallium in MOS2 RGO, this is the composite. Then we can say this is the amorphous nature of the material is going to increase. Things are here. So this is the things is coming. This is the, you can say this is the disorderness. You can say disorderness is going to increase here. Then other is the some same efficient image. You can see this is the very good efficient. This image is done, ARF. JNU completely we done, these things. And this is the HR time image also. This is the we done here. You can see this is showing. And this is other, this is the, we can take, some frequency versus, these things are coming here. So this is the, take vector analyzer. Finally, this is the, you can say, this is the EMI shading due to reflection. This is a different wavelength. This is not stable, so that's why it is not good. EMI shading due to absorption, it is good because it is stable. Then what? If you see the total, then this is, this is the around 20. If you see, so this is here. Then how we can explain? This is the systematic diagram. You can say take, this is the things here, GDMOS2, this is the transmission, multi reflection, this thing. Why last work is this. This is the, work, published in ACS Applied Material and Interfaces. Here what we done, we take, this is a nano hybrid composite really. So if you see, we take CNT MS2 RGO nano hybrid, and then this is the, we take CNT here, then string, then we take, this is the MOS2. These things are here. This is the autoclave. I heat it at 220 degrees centigrade. Then finally we get it. This is the XRD confirm, formation. This is the same image. You can see the, this RGO and MOS2. Here, if you see, this is the MOS2 RGO. Finally, you can get some, this is the CNT MOS2 RGO. CNT, you can see some surface. You can see the some CNT here. And this is the time image. You can say for, this is the for RGO. Then you can go MOS2 RGO. Then this is the for MOS2 RGO. Then if you go for high resolution, then you can get, this is showing CNT MOS2 RGO. Then CNT also, you can see it here. Then we done, this is the EMI shielding. If you see, this is the EMI shielding due to reflection. This is the for MOS2. This is only around, 3 or 4. If you go for MOS2 RGO, it increase around, this is the 5. But if you go for higher, then, but if you take for total EMI shielding due to reflection and absorption, this is around 40. So this is good result if you see here. And how we can understand this? This is the, lot of things are here. This is the, this is the, you can say this is the CNT, this is the RGO, net is here, then this is the MOS2. So migration of electron is electron possibly here, hopping of the electron, dipolar things are also here. So a lot of, multi phenomena we have here. So that's which is coming here. So now I am ending my talk. This is my, this work is most of work, you can see this is for my students' work really. During PhD, they did this work really. And this is why if students are here, this is the collaborator, this is the things are here. Thank you very much for listening my talk. If yes, right. If any query, please let me know. How? Yeah, you want?
No queries, no? You were asking for questions?
We'll ask if anyone asks.
Any questions? Thank you so much, sir, for your insightful talk. Your valuable thoughts have truly enriched our understanding. We have now arrived at one of the most exciting moments of today's events, the announcement of the winners. We witnessed incredible talent and dedication from all our participants across various competitions. Starting with the essay writing competition, here are our top performers from the three different languages. From Urdu, it is Sanjida Khatun from Education and Training. Okay, so she's not there. Right. In English, we have Minhaj Ahmed from CSCN, CSC RCA. In Hindi, we have Nargis Fatima from Zoology. I request the chief guest to give away the prizes. Next. From the photography competition, second place goes to Bushra Siddiqui, MSc Botany. I request Professor P.F. Rahman to please give away the prizes. First place in this category goes to Amara Nishat, MSc Botany. Now from science short film making competition, the second place goes to Javed Ahmed, MSc Botany. I request Professor Maqbool Ahmed to please give away the prizes.
See, this just I would like to make announcement that no doubt he deserves Mr. Javed because he himself has developed one YouTube channel also. So nowadays he is uploading some watering related all activities, you know. So he deserves a huge round of applause once again.
First place in science short film making competition goes to Nabil Ahmed and group. Basically, it has Hilal Ahmed, Farhan Anwar, Asjad Hussain, Ashfaq Ahmed, and Rehan Ahmed from BWalk. And yes, thank you, sir. Sir, there's one more competition. Please, sir, stay. Yeah. So our next competition is Science Conceptual Concept Startup. The second prize goes to Irfan Ashwaq and group. I request Professor Najmul Hassan to please give away the prizes. First place goes to Aisha Begum and Group, MSc Botany. Sorry. Sir, Najam sir, please. Sir, one more prize has to be given. बोला ना, startup. Science conceptual concept startup. खत्म हो गया हो गया इससे रेडी हो गया Thank you, sir. To express our heartfelt gratitude, I now invite Dr. K.R. Maruti for the vote of thanks.
Honorable Vice Chancellor, esteemed Professor Kedar Singh, JNU, respected Registrar Sir, Dean, Professors, colleagues, non-teaching staff, and dear students, good afternoon. I am honored to deliver vote of thanks on behalf of MANUU School of Sciences and present everyone today here. First and foremost, I would thank to our visionary leader, Honorable Vice Chancellor, Padma Shri Awardee, Professor Syed Anul Hasan sir, for their support and guidance. Thank you, sir. I would express my deep gratitude to Professor Kedar Singh, former Dean, School of Physical Sciences, New Delhi, JNU, for taking time to travel from a long distance and delivering a insightful, thought-provoking talk. For your expertise, clarify the thoughts and deep knowledge as shared with us today is truly enriching our understanding. Thank you, sir. I also express gratitude to our registrar, Professor Ishtiaq Ahmad sir, for your support. Thank you, sir. A heartfelt thank to our esteemed Dean, Professor H. Alim Basha sir, for guidance to execute this program. Thank you, sir. I also express gratitude to all faculties and sister institute staffs of MANUU presenting in National Science Day event. Thank you, sir. Thank you, ma'am. I also extend our sincere thanks to all faculties of School of Science for supporting to organize this event. Thank you, sir. Thank you, ma'am. A special thank to juries, Dr. Miraj Ahmed Mubaraki, Assistant Director, MMTC, Dr. Rashmi, Dr. Ira Khan, Dr. Danish, Dr. Afsa, for evaluating all the events. Thank you so much, ma'am. Thank you so much, sir. Heartfelt gratitude to director and staff of IMC MANUU and staff for making this event a live streaming and all. Thank you, sir. Thank you. Last, I would like to thank all our active participants engaged in today. All you made this program as a grand successful, truly a special event. Thank you. Thank you, one and all.
Thank you, sir. As we conclude today's event, I request everyone to rise for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उज्जल जलज तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगल दायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you all for your participation. Students can take their refreshment from the entrance ground floor. The refreshment for